Right. I thought this evening I'd quickly go over. I'm going to start doing some various small snippets, techniques, programming information that's useful to know that hopefully will come in use. Some of it you may already know, some of it may not. So, yeah, this evening I'm going to do a quick bit on the dot product. It's very useful, used a lot. Many programmers use it without really fully understanding it, but it has got a lot of practical applications, issues like lighting calculations, things like that. You can use it for line of sight. So yeah, it's sometimes thought to be a bit complicated when you first look at it, but once you understand it, it's really quite straightforward. The dot product. These would be vectors, 2D, 3D. It works in pretty much any dimension. So we'd say the vector A dot B is equal to the length of A times the length of B times the cosine of the angle, theta. It's a bit like a theta sign. The other way of writing the dot product, if we were doing, say, 2D vectors, would be the dot product A dot B is equal to AX times BX plus AY times BY, where X and Y's are the components of your vector. Now, this is useful because this is how you program it most of the time. When you use it from within classes, if you're in Unity and such like. Hi, Colin. Probably going to do some SAM stuff after this, but so I'm just doing a snippet on the good old dot product. So you'd normally see this in code, but I just clear these off. Right. Normally, you would, let's say, this is the length of vector A times the length of vector B times cosine. Quite often, when you use the dot product, it's to determine if things are looking towards each other. So what this would normally be is these would be unit vectors. So normally have a little hat on them. Say a unit vector is any vector that's got a length of 1. So what this would then come back to is 1 times 1 times cosine of theta. So obviously that then just comes down to cosine of theta. So what we can quite often use that for is it's used, as I said, for lighting, because if you take the normal, if this is a surface, oops, didn't draw that very well. If this is a surface and this is the normal, and we take a light, so it's a light source, and we take this, and we take the, if these are both unit vectors, you do a dot product between them, so A dot B. Let's say in this situation, they'd be unit vectors. You'd get if you do the AX times BX plus a BX plus times. So let's write it out again. So if on this we've done AX, we'll take it as 2D. AX times BX plus AY times BY. That will give us the cosine, providing these were unit vectors. This is quite nice because it gives us a cosine. The cosine of value happens to, if you remember your cosine graphs, Cosine starts, this is at 0 degrees. Oops, that's a sine graph, sorry. So your cosine graph is a bit like this. This is 0 degrees. This would be 90, 180, 270, 360. So when this angle here, hopefully you can see my mouse pointer. When this angle here is, when the light is directly above shining down on the surface, the angle will be 0. The cosine gives a value of 1. And as it comes around to the side, when it gets to when the light comes to this sort of area, this angle here would be 90. So the cosine gives 0. Similar on the other side, if it came down here, and our light was over here, this angle would be 90, so again it would be 0. So between these points here, the dot product, if this normal of the surface and the normal to the light, if they are, sorry, the normal to the surface and the angle to the light, if they are both vectors of unit length of 1, it will give us just cosine, which goes from 0 to 1 and back to 0, which is very useful to multiply the colour of the surface pi. So when the light is directly looking towards the surface, it gives us 1 times the colour, it gives the full colour. If you're using values of 0 to 1 to represent your colours. It's a scalar. 0 to 1, full brightness, back to 0. The other thing it used to be used for is you can also use it when it's down in this area, because we're in this section of the graph here. This is the values are 0 to 1, these are to -1. The values will be negative. The advantage of that is you can tell if the light's behind the surface, or quite often you used to use it. You don't tend to use it as much now because 3D hardware does it for you, but there are still circumstances it's useful. If you do an angle between, say, like the camera and the normal, if the dot product returned you a negative value, you know you're at the behind the surface. This is why a lot of times in old games there used to be secrets by, if you managed to get behind a room, you wouldn't obviously see through. You could see through the walls because they're all single-sided. Still happens today. Polygons are rejected very quickly based on back face culling. It's just one of the ways to see it is to check the angle between your view and the normal of the polygon. If the dot product between the normal and the angle of your view is negative, you're looking at the back of the polygon. If it's positive, you're looking at the front. As I say, it can also be used quite usefully. Because it gives you this angle, you can use it if your enemy's here. Here's our little man, and he's looking this direction. It's very easy to say, find an angle to a point. Say this is the enemy, this is the player. Then we might want to know, is this line here? This is the line between us. Is it within a view for us? Or is it a viewing angle of the enemy? The enemy can only see us if it's within a certain angle. This is sort of his range of vision. So you could sneak up on the enemy in this sections here, around this point. But if he saw you, if he was in this front of his view field as such, the dot product's very useful because it gives the angle. What we'll do in a little while is we'll do a quick example of how to do this in Unity. As I say, the other thing the dot product could be useful for is projection of a vector. So if we've got this vector here, and we'll call this one vector A, this one's vector B. This will be cosine of theta. If A isn't a unit length, so it's not normalized, this part here, different color. This part here wouldn't be 1 because it's not a unit vector, hasn't got length of 1, therefore this would not be 1. So what we would actually end up with in that situation is we'd end up with A dot B, we'll keep B as a unit vector, equals the length of A times cosine of theta. And if you remember your trigonometry, which is where a lot of this comes from, we turn this to a right angle triangle. Cosine was adjacent over hypotenuse. So this is the cosine of the angle, this is the adjacent, and this is the hypotenuse. Rearrange this. We know the length of this because this is our vector that we haven't got as a unit length. So we end up with the length of this. Rearrange this one to give us that, would give us cosine of the hypotenuse equals the adjacent. So what it actually does, cosine of the angle times hypotenuse, which is A, so cos theta times the length of A, becomes this length here, which is the projection of A onto B. But that is effectively A, length of A, multiplied by the dot product of A with B, where B is the unit vector. It projects our length A onto the unit vector, so we know how far A is moving this direction. Might seem a bit, why would you need to know that? Well, one very good reason for that is you've played first-person shooters. We've got a wall here, and here's our player, and we want to move. Oops, using a multicolored pen. This is our player, and they want to move this far. We're trying to move that far each frame. Normally, you wouldn't be allowed to move that far because you're going to hit the wall. What we actually want to be able to do is project how far we are allowed to move by projecting the distance. This is the bit we actually want. We're effectively deconstructing this into its two components, its component along the wall and its component away from the wall. We are interested in this part here. The tighter the angle to the wall, the smaller this, the closer you are to sort of directly running into the wall, the smaller this will be. And so we actually just do this movement. That's why as you straight to the wall, the tighter the angle you are to the wall. If you're very close to 90, you don't move very fast along the wall. If you come in at the angle of the wall, sort of a shallow glance on the wall, you move fairly much at full speed along the wall. But to do that, obviously, you need to find out how far you were going to move in a frame, project that bit back onto the wall itself, and that tells you how far you can move along the wall. So there's various applications of the dot product. And I say that's done by using this, where one of the vectors, in this case it would be the wall, would be the unit vector. Be a lot easier because you'd pre-generated the maps, so you'd have stored the normal of the wall, and you can, well, you probably wouldn't store the normal of the vector along the wall because you could convert it to the wall itself. Using the dot product, A dot B. And I say where A is a 2D vector, x and y, and B is a 2D vector with x and y. The dot product is literally ax bx plus ay by. It's nice and quick. With examples such as like this enemy, for instance, we would where we're using the so I switch the eraser on. Where we're using the cosine, we're going to be checking against an angle. We would not then use the acos function because we could take with the dot product we get the cos, we get the cosine value of the angle, not the angle itself. You can use acos to give you back a value in radians to convert to degrees, so you can compare it whatever this field view you want is. Normally you wouldn't do that. What you would then do is you would say this angle would be 70 degrees. you wouldn't store it as 70 degrees, you would store it as the cosine of 70 degrees. You'd pre-calculate the angle into the cosine, and then you can just compare the values. What I'll do is I will load up Unity, and we'll hopefully be able to quickly do an example. So, right. So hopefully now you can see Unity. I've just created a blank 2D project. What I'm going to do is I'm going to literally add 2D sprite. One second while I pull in some, graphics. Just need anything just so we can see the I don't think you can see me browsing through the files, but I'll just put in two sprites. There we go. I've brought in a red and a green tank. So, yeah. So we've got the new sprite. I'll select that as this little tank here, and I'll also add on to that. We'll call this the player, and we'll add a new component to this. I'm not sure if you're seeing some of these. Let's see if I can fix that. Don't know if you can. Oh yeah, you are. Hard to tell sometimes with software what you can see. So I've created a simple player, and I'll also create a new sprite, and I'll drop the red tank on. So we've got another sprite. Again, I'll add a new script called enemy. Now, that's all we're going to use for this. It's going to be relatively straightforward. I think I'm just going to have to bring in another window so you can see the code. Right. Hopefully now you can see the code editor. Let's see if I can make it a little bit bigger. So it's a bit easier to see the code itself. And the trouble is with streams, sometimes it's a bit horrible to see the code. Right, let's try that. Okay. So we've got our two classes. We've got the enemy and we've got the player. the first thing we want is in the player. It's going to be very basic. We just want to be able to move. So if we are using key code left arrow, so if we're pushing left, we're just going to take transform and rotate. Because it's 2D, it's forward. We want to rotate around forward. And we'll rotate 2 degrees a second. More than enough. And if we're pressing right, we'll get minus 200. If we get key code up arrow, what we want to do here is we want to do the transform, take a position, and onto that. Let's say because 2D forward is sort of in and out of the screen, which is why we rotate around forward because we want to rotate the screen. As far as moving up and down the screen, it is up. So we want to up, and then web speed. Again, obviously, we need to multiply it by the frame delta to so it does it the same speed all the time. And just so you can see the direction of things, transform. We'll draw a line, just a debug line from where we are. Still keeping the hue in colour. So literally pushing left, rotate, left, pushing right, so rotate right. This is just if you push forward, and forward, and this is just a debug. Hopefully, all being well, we now flick back to Unity. If I run this, well, I'll put that on the red tank. But there's our green tank with the player script on it. See if I put these the right way around. Oh no, either. I thought it's strange. It's because I've put all this code in the enemy class. In a second, I'll just take that out. That's a bit confusing otherwise. We'll put it in player class. And then flick back to Unity. So this is the enemy. So this is the enemy is red. Send 5 by 0 by 0. This is the player. We'll leave them at 0. They've got the player script, so if we now run it. Oh. So we can move around, we can rotate left, we can rotate right. One thing I've noticed is the sprites flipped, so we'll just flip that over. Do the same on the enemy tank. Right, so now what we want to do is we just, first thing we'll do is just get the enemy to sort of wander around. So if we go back to our code, now a little, not much more complicated, but a little bit. We're going to want to. We're going to need to learn a little bit more about it. First, one thing we're going to need in a proper game, you certainly wouldn't do this. I'm going to get a pointer to the game objects player. You may do this. I don't know. Depends on the game. We're going to have a distance the enemy can see. We'll make this 8 units, and we are going to have an angle that the enemy can, a view cone angle. We'll set it to 20 degrees. Now I've set this in degrees. I'll leave it as degrees because it's a little bit easier to see and understand. It just means we have to do a little bit of maths. But as this is a very simple example, it doesn't matter. The other thing is going to keep track of. Well, I'll leave it as public. Last scene. This will be the point that we store the last scene position for the player. Because what we're going to do is, when he loses track, he'll just sort of meander around, sort of patrol around the last place, and we'll have a target, which is where the player's head, where the enemy is heading when he's wandering around. To start with, we'll just set them both to the transform. When we start the game, we'll just set both the transform of the object itself. So at the moment, he's not seen anywhere. He's trying to head to where he is. So in the update, straightforward for now. Let's see if have we reached our target. So let's just get distance between our current position and our target position. If that is less than a certain value, a small value, just because of obviously inaccuracies with floating point, you never really compare exactly with 0. So we'll check with 0.1. At this point, we've reached our tracker point. So we'll pick a new spot to move to. This is generally if he's lost. If he's not seen the player, we'd cover in this. So we'll pick a random point away from where we are. So target is going to be our last seen position, and then we'll add on a certain amount of rotation. Oops. Times by, doesn't really matter, a certain distance away. So we'll say move maximum 5 units away. Try to be accurate, we'll put this in here. What we need to do here is now work out a rotation. Can't be a float, have to be a quaternion, just to be able to rotate around a vector. And all we need is a random number between 0 and 360. So actually just picks a random point. So when we've reached it, pick an angle between 0 and 360, pick a distance 5 units away from where we are, and there you go, that's our new target position. If we're not at the new point, then we want to move towards it. So in this case, we're not there. We need direction, which is simply target minus transform position. I'm going to make the thing rotate as well, just for completeness. So we need to work out the angle towards the target point. For this, I'm going to use ATAN 2. I've already done a video on ATAN, how to use it to form a look at. So I won't go into much depth. The only difference I'm using here is usually with ATAN, it gives you the direction to the right, the angle based on the direction to the right. I want to use it as an actual physical direction. So rather than doing the usual y comma x, doing y divided by x, I'm actually going to use negative x divided by y. I'm not going to do the divide. That's why I use ATAN 2 rather than ATAN. You don't do the divide, it handles the division by 0 for you. And ATAN returns a value in radians, so we just need to multiply rad by 2 degree to give us a value in degrees. So that gives us the angle we need to be pointing to move towards our new target point. What we'll do is we will create a quaternion to do the rotation based on angle now. Again, we're going to rotate around forwards in and out of the screen, not up, which is sort of direction we'd move. So it's angle axis. So this would be angle. So this is a quaternion based, and we could just set that directly into our transform rotation, but then it would snap. So what we do is we just, it's not ideal. Just makes it a little bit nicer, but we'll lerp. We could slurp could potentially go away from 3D, so we'll continue with lerp for this example. And time. How fast we want to go. So it'll sort of interpolate to that point from our current rotation. And then all we do, similar to the way we've done the player, we just need to transform that up. Times our speed. We'll go a little bit slower than the player. Just to make it so we can run away from them, otherwise they'd always follow us. I'll draw a similar ray. So from our transform position, transform up. We'll do it based on the view distance. And we want that to be, we'll do it in yellow. And might need to put faults in for depth test, but that should be enough just to make the checkable builds. Double to float. Ooh, forgot the Fs. Too much shader programming. Okay, so if we now flick back to Unity, if we run this, hopefully what we'll now see, we haven't put any logic in for the player, so the enemy's just wandering around, picking points to go to. Let's see if we can just make this screen a little bit bigger. There we go. get a bit better view. So you can see he's just wandering around, and he's actually managed to get quite close. What's happened there is he's actually got really picked a point very close to the last time. So this probably is. It's close enough. The new target point is far enough away that he's trying to get there, but so close he can't actually get there quickly. So we'll take it, we'll make it a little bit bigger. But that just gives us an enemy that walks around. Now, because we're trying to show the dot product, what we will do is we will have a little function called cPlayer. Can cPlayer, and this will just say yes or no. So normally, no, we can't. What we'll do here is if cPlayer, if we can see the player, the easiest thing to do here is we just basically want to say last point we saw the player is in the last point here will be the player.transform.position, and we'll set the target to last seen just so the tank goes towards it. Obviously at the moment this will never happen because it returns false. One thing else we can do with debug raise down here is we can, because we'll see, well, let's do it without the view frustum to begin with. So we just want to say for seeing the player, again, we need to know how, we need the vector between us, so we'll just do vector3 is equal to the player.transform.position minus r transform position. So that's the vector, basically the magnitude and the direction between us. So if we just take the magnitude, so that's the length of the direction. So that's less than the view distance. Then we can just say we return true. We can see this. So that's a very crude. It's not using dot product yet, but what it's saying is, can the tank see us? What I'm actually going to do is take that as a variable, and down here we'll use a red or a yellow. So when it goes red, he's seen us. So if we now flick back to Unity, hopefully this time when we press play, we need to select the enemy and just say which game object is the player. So just drag and drop the player on there. Let's pull the camera back again because I've done it in play mode. Hopefully we'll. Right, oop, he's seen us straight away. But because it's done distance test, I've got to get right away, but I've got to be far enough away before he stops seeing me. I can't, oh no, too close again. But I can't sneak up on him from behind, because as soon as I'm in the circle that he sees, so he's now chasing me far enough away. Oh no, again, he's after me again. So that's all based on just the distance, whereas we want to do a view cone. So if we come back to our code, let's first of all draw the view cone. Just use some very nasty maths to do this. Doesn't need to be pretty. So the right angle is a quaternion Euler angle. Now I'm going to say the view angle is the amount to the left and to the right. So we've set it to 20 degrees, so it means we can see 20 degrees to the left, 20 degrees to the right. So we've got a 40-degree view angle. And then what we'll do is we'll draw a new ray. We just need to multiply other angle, and that's to the left, and we'll do one to the positive as well. So hopefully what we'll now see, I'll colour them green just so you can see the two-ray cone. So what this will now give us, if we flip back to Unity, hopefully, as you'll see, there he is. He has now got a view frustrator. That's the view angle he can see. That's the view cone that he's got, visibility cone. But we now need to use that. So this is where, at last, I don't know if I show you that. I think I forgot to enable your view of it. So I'll quick run it again. Yeah, so you can now see the view cone. But as I say, it doesn't matter because it's not checking it. So even though I'm outside his view cone, because I'm within the distance, he's still following me. So if we go back to the code, we just need to update our... we'll quick and easy check first. Always do knock out the more complicated maths first, with a simple check first. So what we need to do here now is work out the angle between us. And this we need the dot product between our forward, or up vector, because we're in 2D, and dir. Now, remember, we need to normalize. We need the normalized vector. If we don't use the normalized vector, we won't just get the cosine, because remember, cosine is equal to the length of A times the length of B times the cosine of the angle. We only want the cosine. So as long as both of those are these transform vectors are, so we just normalize our vector. That gives us just the cosine. As I said, normally, for now I'll do it the slower way first. I'll use ACOS. We can take the ACOS of the angle, because we want to know whether it's between ours. At the moment it's the cosine of the angle. ACOS will give us the sine angle. And we have to multiply it by round to degrees, because we've stored ours at degrees, which we can do. That's less than our view angle. At that point, we return true. So what we've done here is we've used the dot product to work out the cosine of the angle between our up and the direction. I think we'll do is we'll draw these debug. We'll do a debug ray draw, just so we can visualize them as well. Form dot position. Transform dot up times view distance. Color yellow. And we'll do another one. This time it's the direction normalized. Right, so we'll use that for now. So if we now flick back, just check files. So flip back to Unity. Now it's checking the view angle. So what you're seeing at these points, the green are his viewing cone, the yellow is his forward motion. Once we get within the viewing distance, additional yellow lines pop in. One's the same as the other, so which is the normalized distance. Off screen. But as you can see, I can sneak up. I can sneak up behind him, and this angle is always greater. If I get inside that view cone, he should really track us for a bit longer. You see, it turns red because he can see us now, but as soon as I step outside that angle, oh, he's lost us. And he's back in. So that's all there is to adding in this view cone. It's this one bit here. As I said, we could use cos view angle, and rather than having to do all that math every time, we could just pre-calculate the more expensive maths bit. We actually want to store this as the mathx.cos. I know computers are fast enough now. I suppose old habits die hard. Cosine isn't horrendously slow in modern days, but every cycle counts. Just because the computer's fast enough doesn't mean you have to waste the cycles. Take a bit of pride, try and save some cycles when you can, because later down the road you may need those cycles for something else. So it's better to get into a habit of trying to save them while you're able to. So now, because we've now calculated the cosine of this angle, we don't need to do the ACOS here, which is a lot more expensive than just cosine. We can just compare it between the two. Extra parentheses we don't need. And that should, go back to Unity, it should give us exactly the same thing. So we can still run around and you can't see us until we get inside. Ooh. See, made a mistake there somewhere. He's not seeing us. I imagine what I've done is just a very simple error somewhere. Oh yeah. Obviously we're specifying the value in degrees, whereas cosine wants the value in radians. So actually I need degrees to radians in that, not radians to degrees. So there. Simple fix. Flip back and run. And now I'll use the right screen. There we go. So yeah, so you see this until we get a size view cone. That's all day down to the dot product. Hopefully that's been some help. As with any of these things, if you have any questions, drop me an email. I'll put the email on the slides. I'll upload this to YouTube. You find me on Facebook at APV Developer. So if any questions, yeah, let me know.